Okay, let's get started. So today is our great pleasure to have Professor Yifei Long from UT Dallas here. And Professor Low is an associate professor at the Mathematical Science Department at UT Dallas. And she received her PhD at UCLA. And after graduation, she was a postdoc fellow at the School of Electronic Computer Engineering, Georgia Tech, followed by another postdoc training at UC Irvine. Professor Low received the National Science Foundation Career Award 2019. Her research interests include compressive sensing and its applications, image analysis, including medical imaging, hyperspectral imaging through turbulence, and non-convex optimization. Okay, Yifei, I give you full control, please.
Okay. Thanks, Rongje, for your invitation and introduction. Today I will be talking about my recent work on one of my research interests, which is hyperspectral imaging, using graph method. So first of all, let me see. I'd like to acknowledge the co-author of this work. So actually, this work initialized at ICER. So we spent a week at ICER and we produced 2 papers. So it's a very productive week. And I highly recommend if there are female students or junior faculty in the audience, you may pay attention to Wisdom. Can you see? Yeah. So this group is called Women in Data Science and Mathematics. They usually have every other year, not this year, unfortunately. Yeah, so they will have a 1-week program and it's very productive. Yeah, so my talk today will based on 2 works. One is using graph Laplacian, and the other is use graph total variation to do hyperspectral unmixing. Okay, so the outline of my talk goes as follows. First, I will talk about some background information, including graph calculus. So basically, we extend all the calculus with regular Cartesian grid into a graph domain. And then I'll talk a little bit on PDE, which is the relationship between total variation and the Ginzburg-Landau functional. And then I will talk about what is the problem of hyperspectral mixing. Like there's some existing classical method for hyperspectral mixing. For our method, as I mentioned, I will talk about 2 regularizations. One is graph Laplacian, and the other is graph total variation. So basically, it's go from the traditional like image processing, extend H1 semi-norm to graph Laplacian, and then the image, the total variation to graph on the graph. And I will show some experiment followed by conclusion. Okay, so let's get started on the background. So this is a very fundamental definition for graph. So graph consists a set of elements called nodes or vertices, and also it has a relationship between 2 nodes. It's called edges. So there's a set of nodes, and then some of the nodes will be connected, and that connection is called edge. Okay, so okay, formally, a graph can be defined by a set G, which contains these 2 sets. V is the vertex sets, and then E is the edge sets. And then we denote Vi as the ith element, and then Eij is the edge go from Vi to Vj. So if we specify the direction, like Vi to Vj and Vj to Vi are different, then we will have Eij and Eji. But if we consider undirected graph, then like it's just the edge that connecting Vi and Vj. So whether it's directed or not, that depends on the application. In my case, it is undirected. Okay, and then we can also assign a weight on each edge. So we can define Wij on the edge or on the connection, the edge connecting Vi and Vj. Okay, so we define the degree of a vertex, which is summing up all the weight that is connected to this vertex Vi. So we sum up all the weight that is connecting with connection to Vi. So that is the degree matrix. Okay, so next I'm going to talk about the derivative on graph. So to make it more rigorously, let's define HV as the Hilbert space for function defined on the vertex, and HE to be the Hilbert space on VE. So we can formulate inner product, derivative, integration, adjoint operator. Okay. We need to assume that the weight function is non-negative and symmetric. Symmetric means Wij is equal to Wji, and non-negative means every weight element is non-negative. It's non-negative is different than the semi-definite matrix, meaning that the eigenvalue is non-negative. But here we want each element is non-negative. Okay, so this is the derivative operator or difference operator. So it is a function mapped from the vertex domain to the edge domain, right? So we have we fix the f is defined on the vertex, so we have fvi, fvj, and then after this mapping, we will map to a function that is defined as a edge vij. So this dw is a mapping from the vertex to edges. And the definition is given by you take the difference between the function on two vertices and multiply by the square root of w. So that's why we need to make this w non-negative, and also we need to make it symmetric, so that later on when we look at the adjoint operator, we can interchange vi, vj. Okay, so this is the difference operator, and then here is the gradient. So the way to interpret difference and the gradient is difference is derivative at a point, vi. And then the gradient operator is putting all those derivative in terms of a vector. So it's like derivative as a function. Okay. So this page is about derivative. Okay. So if w is like a constant, then this becomes the standard finite difference game. Okay. Next, we will discuss the integral and inner product on graph. So we know from standard calculus the integration is summation, and here on graph we just summing up all the vertex as a integration. And similarly for edge, so we sum up all the connecting edges to be the integration on edge space. Okay. And then once we have the integral defined, we can define inner product, right? So by standard calculus, the inner product is defined to be summation f times g of x, ex, right? So here by replacing integration with summation, we get the inner product definition here. For vertex, it's just summing up all the vertices, and for edges, you summing up all the connected edges. Okay, based on the integration, why do we care integration? Because we want to define adjoint operator. So by standard Euclidean distance, so if we have a x, a y, it is equal to a transpose or a joint of a x, y, right? So this is the standard inner product. Now we look at the graph domain. So it will be, we want to define the adjoint of dw. Okay, and notice that this inner product are defined on different spaces. On the left side, it is on the edges. The right side is on the vertices. So that's why we need to define properly this two inner product. Okay, so based on the inner product, based on the derivative operator, we can actually derive, sorry, too much. We can derive the adjoint operator, what it looks like. So after some manipulation, we can get the inner product. The adjoint of derivative has this form. So it has some duality, right? So if you remember, the derivative is fvi minus vj multiplied by the root of w. The adjoint is a gvij minus gviv. Anyway, so you take the difference between g and multiply by the square root of w. And then we need to make sure, we need to assume g is the w is symmetric, so we can have this nice form. Okay, so I think, okay, so we have defined the derivative, we have defined the adjoint, which is the divergence operator in calculus, right? Based on these two operations, we can define norm. So for example, we can define the actual semi-norm, this one. So if you don't have this W, right, this is the standard H1 seminorm. It is the gradient. It's basically like this. You have WF, WF in a product, right? And then you can expand this gradient F on a group setting to get the form. And then the next one is the total variation, okay? So by standard calculus, we know that if we take the derivative of H1 seminorm, we get Laplacian. Same thing here. We can take the derivative of this graph, H1 seminorm. We can get this is so-called graph Laplacian. And this graph Laplacian can be discretized that as a matrix L multiplied by F. Okay, and then this matrix L has this form. On the diagonal, it is the degree of for every node, and on the off diagonal, it is the negative of W VI Vj. Okay, so I think that is all the calculus relevant to graph. It includes derivative, integration, divergence, norms, and derivatives, a gradient. So any questions so far? If not, I will move on. Okay. So the big problem or challenge in graph-related application is this Laplacian operator is big. The weight matrix is big. Think about if we want to use a graph to do image processing, and let's just assume image is 100 by 100 size, which is tiny compared to recently a few thousand by a few thousand. So if we just consider an image of 100 by 100, and then we think every pixel is a node on the graph, then this graph will have 10,000 nodes, right? And then remember the graph is pairwise in like connection. So this graph will be 1,000 by 1,000 matrix. It's very challenging and time consuming to compute this weight, and also its storage is also a problem. So weight computation of a fully connected graph is a bottleneck to many graph-based algorithms. So to accommodate for big data, here is a Nystrom method, try to approximate eigenvalue and eigenvector of this W by only using p-sampled data points. And then presumably p is much smaller compared to n. So what it does is instead of computing pairwise, so we use this weight to measure the usually the similarity between two nodes, right? So instead of doing every pair, which calls as L-square calculation, we only compute p point to the rest of it. So we have a block matrix. So this is p, and this is n minus p. So we only compute this portion of the data, p versus the rest, the similarity. And then we will use the Nystrom method to approximate this big diagonal, this big square matrix. Okay. So this W is a symmetric. So W11 W21 is equal to W. So these two are the same. So we just need to approximate this question mark. Okay, and then approximation is given by this form. Yeah, so and in fact, we're not just computing the approximation for weight. We're actually doing approximation on the Laplacian. So previously we have L is D minus W, right? Degree matrix minus W. And we do not just use this L, we use a normalized symmetric Laplacian by doing so the negative half multiplied by the minus W and then multiplied by the negative half. So we will get identity minus this. So the good thing about this LS is it's symmetric and it enjoys fast way of doing singular value decomposition on from the Nystrom method. Okay, so that matrix is what we will be using for our application.
So if I can ask a question?
Sure.
So what do you have any assumption about W besides W just symmetric?
W is the negative and symmetric.
But But is it a reason like you use this low rank, relative low rank W?
Yeah. So because we need fast. It may not be a good. So okay, mathematically we cannot guarantee it is a good approximation, but numerically we find this W works pretty well. We only use like 1% of the data to approximate. So we want fast, and we want to, basically we just want fast. I think the speed is important, considering we have a big dimension to process to compute the weight. We need a quick method to do the weight computation.
So you
whether it's accurate.
Sorry.
Go ahead.
Yeah, you want to say for your application, that specific W, this approach work, but this is not may or may not be accurate for general.
That is correct. Okay. But Andrew Bertuzzi has a lot of paper on graph-based learning method, and based on her experience, like for machine learning and for like this kind of hyperspectral unmixing, this approximation is good enough.
I see.
Like because when we compute this weight, we use some kind of approximation, right? So and then why not we approximate even more?
Sure.
So we don't know what is the ground truth like weight for the future for the analysis or for the application. So we just do approximation of approximation, and it works pretty well, I must say.
So in your setup, each node is an image. Is that right? When you do the
No. Each node is a. I'll go talk to that in a few slides.
Yeah,
but
sure.
It's every pixel. It's basically every pixel. Yes, you are right.
Okay.
For every pixel, I think it's a node. Yes.
Okay. Thanks.
Okay. So here is a slide about classical total variation and Ginzburg-Landau. So assuming you probably know the total variation, let me just quickly talk about the Ginzburg-Landau energy. So this is the Ginzburg-Landau. It has two terms. One is the H1 semi-norm, and the second one is called double potential. So it looks like this. This double potential will attract your point to this this well, right? This double well. So it will attract the point to take. So here it's either 0, 1. So I want the point to be 0 or 1. And what the first term help us? The first term is a like smoothing factor. So I want my point to be 0 and 1. And between 0 and 1, I want to have a smooth connection go from 0 to 1. And epsilon just control the scaling of this from 0 to like the transition period. Okay, so this is epsilon. So epsilon control like how quickly you go from 0 to 1 or from 1 to 0. And they often use this Ginzburg-Landau to do like binary classification, either 0 or 1, and in between you want to do a smooth transition. And then the good thing about Ginzburg-Landau is it converts to total variation in gamma convergence sense. So as like epsilon goes to 0, the Ginzburg-Landau will converge to total variation up to a constant. That is a classical result in PDE literature. And then we borrow that and extend it onto graph. So the H1 semi-norm will be written as U, like, H1 semi-norm can be written as the Laplacian U, inner product between U and the Laplacian of U. And then the double well, we can also have double well. And then just to revise the Ginzburg-Landau on the graph, and then using the graph settings that we discussed. Okay, and you may wonder, how do we solve this Ginzburg-Landau? It seems complicated. Well, it's better or faster than total variation because we can just use a gradient descent. So here is a gradient descent, and because as I mentioned, it's double well, right? Prefer 0 or 1. So after you're doing one step of gradient descent, you just do a hard shrinkage. You manually make it any point larger than 0.5 to 1 and smaller than 0.5 to 0. You can do this separation to two phases. So this is called MBO scheme. And this scheme is very efficient. It usually converges in like 3 to 5 iterations, and it can solve Ginzburg-Landau minimization problem. Okay. Finally, it is about our problem, the hyperspectral unmixing. So let's first talk about what is the hyperspectral data. Instead of color image, which it only has 3 color bands, R, G, B. This hyperspectral data has hundreds or thousands of bands in this domain. Okay, so wavelength domain or spectral domain. And it still have the spatial information. So the drawback for the problem or the challenging challenge problem in hyperspectral data is that although it has a high spectral resolution, the spatial resolution is very bad. I remember 10 or 12 years ago when I was a student, the hyperspectral data, 1 pixel on the hyperspectral data corresponding to a 10 by 10 meter on the ground. So you can think of this 10 by 10 is very big, right? Anything can happen in this 10 by 10 region of area. So hyperspectral unmixing is they want to see for this 10 by 10 region of interest, what kind of material it contains, or what's the percentage of material this pixel contains. Like for example, suppose this is a pixel, right? So this might be 70% of the concrete, 20% of grass, or another 10% of dust, right? So they want to know the percentage of material that is contained in a single pixel. That is called hyperspectral unmixing. You want to unmix one single pixel to the percentage of different material. Okay. So let's talk about this data. So originally the data given to us is a data cube, right? So we have like X, Y, and also the spectral domain. And then we will reshape it to be a matrix. So this is N1, N2, and this is W, right? So I will reshape the 3D cube in terms of 2D matrix. This is every column is a spectral data. So, and then we have N1 times N2 number of pixels. Okay, so that is our data X. And that is provided to us. And our goal is to decompose this matrix in terms of a percentage, as I mentioned. Also, I want to know the spectral signature, like a dictionary, for all the materials that I will consider. For example, like dust, concrete, a tree, water, right? So those materials, I will have a dictionary, a representative spectral information, and I want to also have that. So I want to decompose X in terms of 2 matrices. One is called mixing matrix, which is the spectral signature of a pure material, as I mentioned, like tree, grass, dust, something. And also the abundance matrix is a percentage, say 20% of dust, 50% of concrete, another 30% of something. Okay. So the problem is I want to decompose X in terms of 2 matrix multiplication, S and A. So if we do not know any of them, so it's called blind. So we do not know S. And sometimes S can be obtained or measured in a laboratory setting. But you can see the laboratory setting may not be so accurate if it's outside on the ground. So there is still a need to estimate S more accurately from the real data. So non-blind refers to I don't know S. Blind means I need to estimate S as well. But anyhow, the abundance matrix is always unknown. We want to estimate. Okay. So here are some existing methods I will be comparing later in the experiment. The red is the non-blind method, and then the blue is the other way. The red is the blind, blue is non-blind. By non-blind means I know S. And then something to pay attention is I can add regularizations. As you can see, this hyperspectral unmixing is highly ill-posed, right? So I give you 1 matrix, you need to multiply, you need to get me 2 matrices out of it. So it's highly ill-posed. So we need to add some regularizations. One popular regularization will be doing total variation. And then we can also doing some group sparsity. And there's all kinds of regularization that is imposed for hyperspectral unmixing. Okay. Oh yeah. So to formulate hyperspectral on the graph, we think every node is a vertex on the graph, and we consider fully connected graph by looking at this kind of weight. So if you know the local means, it's pretty much the same as the local means. So you have exponential to the negative distance between x and xi and xj divided by a sigma. So we use sigma to control how similar each node, two nodes are, and then we can adjust sigma. And then there are different metrics to measure the similarity between two nodes. In the local means, we use the standard L2 norm, and then we found in hyperspectral the cosine angle is perform better because it can eliminate the scale impact. So we use the cosine angle to measure the similarity between xi and xj, and then we compute the weight. And then we do not compute, although we want this fully connected weight, but we use Nystrom to only look at the p pair of nodes, and then use Nystrom to expand to the entire like weight computation, or to approximate the weight. Okay. Okay, so that is all about the background. I think I spent more time on the background rather than our method. But I think the main contribution of our work is to putting all those things together to make a very efficient approach to do mixing. Okay, so our another contribution will be to look at two regularizations on the graph. One is graph Laplacian, the other is graph total variation. So here is the regularization I mentioned. So graph, we use graph Laplacian and the graph H1 seminorm interchangeably, because if you take derivative of H1 seminorm, we get graph Laplacian. And also we do not just do graph Laplacian on every. Oh, by the way, we apply graph Laplacian. We apply regularization only on the abundance. We don't do anything regarding the mixing matrix S. And also, we do not apply it directly on the abundance matrix. We apply on the hat. What is A hat? A hat is A normalized by the degree. So the reason why we apply regularization on the abundance hat, not without hat, is this will help us to use a Nystrom method. Remember, this Nystrom will give you the approximation for the normalized similarity. So for Nystrom, we get the LS, not the standard Laplacian. In order to use the fast algorithm from Nystrom, we have to do the hat version. Without hat, it doesn't work. Okay, so that is our regularization. So our regularization is on the hat version of the abundance matrix. And then the rationale why our regularization works is that we assume that we want to minimize the H1 seminorm or the total variation to try to promote if AI and AJ should be similar if Xi and Xj are similar. Meaning that any questions?
Yeah, can I ask another question? So is the degree is the degree quite uniform for your graph structure? Because every node they are connected.
No, but we don't compute this way, right? We only compute P versus N. Yeah, but you are right. It might be similar, but I didn't check.
Yeah, but what I mean is not whether you normalize or not normalize, if the degree is quite uniform, why there's a difference?
So we prefer to normalize it so that we can use Nystrom. I don't think it's exactly the same. There's still some variabilities. It's not exactly. And some nodes may have more similar patches, have more similar nodes compared to others, right? So it's not uniform.
But
so DII is not uniform.
But you're having a
so you can think of if yes, but I only use a subset of the weight nodes to compute the weight. So we don't know whether it's uniform or not. And if you think about it, suppose we have some repetitive patterns, then those weights will be bigger than if we have a rare structures. So it's not I don't think it's uniform. But
I see. Your degree is a summation of the weight. It's not just
it's it's not the yeah, okay, so yeah, okay, now it's
I got you.
So there are two things. One is the adjacency matrix, and the other is the weight matrix.
Yeah,
so adjacency matrix, yes, right, it's the same. But I'm adding up the weight matrix. That's completely different.
Okay, I got it.
But it might be, yeah, no. So the rationale is that this W is has this similarity between X and Xj, right? So we expect that if Xi and Xj are similar, then AI AJ should be similar. So that is our motivation to design this graph regularization. And also by image processing, we know that H1 seminorm may cause over-smoothing, while a total variation can produce preserve sharp edges. So that's why we first look at H1 seminorm because it's simpler than the total variation, but we compare both of them in the experiment. Okay. Next, to solve this model, we use ADMM. So this is our data feeding term, right? And this is our regularization. So as I said, this regularization can be either actual seminorm or total variation. And here we have a bunch of constraints. So by physics, we know that the mixing matrix must be in the negative. So that is by physics. And then by probability, right? So as I mentioned, A is a probability, so it must be non-zero as well. So we have this omega means the non-zero matrix set. And then A is a probability, so it's sum to 1. So we also have sum to 1 constraint. So we have data feeding term, regularization, and feasible set. And then we use indicate function to put the constraint as in the objective function, right? And then we will introduce some algorithmic variable to do ADMM. So, oh, okay, sorry. For Laplacian, we probably don't need the separation. Oh, we still need that. Okay. Yeah. So we need we introduced 2 variables, I think. Yeah. So originally we need minimize with respect to S and A. Now we introduce 2 variables, one for A, the other for S. The reason we're doing that is for every subproblem, we will have a closed form solution. So the remaining thing is standard. We have this minimization. We have these 2 constraints. We form a augmented Lagrangian, right? And then we alternatively minimize every component. And then fortunately, every subproblem has closed form solution. So for the C subproblem, it's basically a least square type of thing. So you just do least square inversion. For S subproblem, you project this thing onto the non-zero set. It's also one step thing. For part A, this is the you need a sum to 1 constraint. So again, you do a least square and then you project onto the sum to 1 and then the negative set. For B subproblem, it's a little bit tricky because it involves the Laplacian. But Laplacian, you already have the singular value decomposition, so it's not that bad. It's also very quick. Oh yeah, so here is summarize all the closed form solution. Right, this is just a max problem. This is the least square inversion. This is a projection onto the sum to 1 constraint, and this is based on the SVD. So you're just inverting the diagonal element. So everything is very efficient to implement. Okay, so that is the H1 seminar. Next, we will talk about the total variation. The difficulty with total variation is it does not have closed form solution for the TV term, right? Not like the H1 seminorm, we can apply SVD. We can apply SVD and doing the inversion. It is TV, it's nonlinear. We cannot do that. So what do? We only need to discuss the B subproblem because the other variable is the same as the H1 seminorm. So we just look at B. We remember I talked about the TV and the Ginsburg-Landau, and then we haven't used it, right? So here is how we can use the Ginsburg-Landau. We do not directly minimize total variation. Instead, we approximate total variation by Ginsburg-Landau. There's something we need to be careful because Ginsburg-Landau, it has double well, right? Meaning that the pixel has to be either 0 or 1. But obviously, we cannot have such assumption for B because A is a probability, right? It cannot be either 0 or 1. So what do? In order to remove this binary restriction, we decompose B bitwisely. So we remember B is a fraction between 0 and 1. We can write this as a binary decomposition. So like 0.5 plus 0.25, right? So we can decompose B bitwisely. And for every bit channel, we apply the MBO scheme. Okay, so here is the detail. We first do binary decomposition by decomposing BI in terms of different channel. And then for every BM, we minimize the Ginzburg-Landau because BM now is a plus or minus, sorry, either 0 or 1, right? So so here is our Ginzburg-Landau, and BM is indeed either 0 or 1. So we can use the fixed point iteration so this three is like the gradient descent. And then after gradient descent, we do a half shrinkage to make 0, 1. And overall, this is very efficient. As I said, MBO only need 3, 5 iteration to converge. Okay. Yeah, so we look at the time complexity. So the major time we need for Nystrom is to do a SVD on P times P matrix. And then we also need to compute the P times N. This matrix W12 is P times N. So the time complexity for Nystrom is this. But this is pre-computed, right? So we just need to compute at one in the beginning, and then the remaining ADMM requires this many complexity, including SS, including all those variable updates. And compared to other methods, because we save a lot in terms of weight computation, so we are better. So here is this compared to this, right? So it's much faster, time efficient. It's very time efficient algorithm. Okay. Any questions before I move on to experiment? Okay. So let's first talk about three metrics to measure the performance. The first one is the standard root means error. We can measure root means error between the abundance and also the abundance and then the mixing matrix. And we can also look at the normalized MSE for both abundance and the mixing matrix. And the last one is only for measuring the spectral matrix. So it's the mixing matrix. We don't tend to use a spectral angle to do abundance calculation. Okay, so let's look at synthetic data where we create this pattern. This is 5 endmembers, and this endmember we obtained by taking 3 endmembers from US geoscience library. So we're just picking 5 elements, and then we make this pattern. And this is the abundance plot. And then that is the first row is the ground truth. And then the second row is the comparing method, including the total variation. This is the negative matrix factorization together with graph Laplacian. This is a very recent method called quadratic minimum volume. Yeah, and then so these are our method, right? Graph Laplacian and the graph MBO, so TV is our proposed method. By comparing all this method, we find the first two, you see the colors different, right? So it cannot get the color scale correctly. And then the QMV, it looks noisy. It's not preserving the, we don't see a lot of squares. Well, compared, like graph TV is still kind of noisy, but I think it's better than this QMV. If we compare graph TV versus graph Laplacian, we see graph Laplacian is over smooth, right? So it's true, it removes the noise, but also it smooths out the important features. That is consistent with in image processing where H1 seminorm tend to over smooth compared to total variation. Okay, so yeah, so that is the synthetic data. And also we have some quantitative metrics. So yeah, so I don't see any. Oh, okay, actually, this QMV, when the signal to noise ratio, so we also add noise. when signal to noise ratio, when we add a small amount of noise, actually this QMV is pretty good. But if the noise is increased to SNR equal to 10, then QMV is not as good as our proposed method. Okay. Do I have? Okay, time will be later, I guess. Next, we will look at a real data set. It's called Jasper Ridge. So we have on the top is the end member, so which is the S matrix, and then I think there are how many? 5. We have 4 elements: tree, water, dirt, road. So we plot the spectral signature here. So this is the S matrix, and then the bottom are all the abundance map. So I want to point out a few things. So this road, right? It's a fine structure, and you can see only these 3 methods using graph-based method. They can preserve this tiny structures of this road. The remaining things, they all failed. Because we use similarities, we can pick up those important information, that tiny structure from this road. So that is one advantages of graph-based method. It can preserve important, even tiny structure patterns. And then, well, I also want to point out some disadvantages of graph method. Say if you see a homogeneous region, our method does not work so well. So you will see it's still noisy. It's not removing completely, right? Where for this STV, this region it's all perfect. It may be a little bit over smooth compared to the reference ground truth. So our method, we just look at the similarity, right? We don't have any spatial relationship. So that is why it does not perform so well on the piecewise constant region. And it's also motivate our future direction that maybe we should combine the similarity and also the spatial total value. So meaning we want to combine these 2 methods. Hopefully we will get better results. Yeah, so that is the
yeah, Yifei, I wonder for for this curves, right? What's the x coordinates? It's just the one slice of it.
Oh, you mean this curve? So the x-axis is the number of spectral index, like the wavelength. So regarding what's the unit, I don't know. I will just plot it. I don't know the unit. Like I think it's millimeter, but I don't really know. It's from But I just plotted. It's like S matrix. It's S. We're plotting every column of S to be the signature of every material.
But this is like for one given pixel, because each spectrum you have so if 200 is like 200 spectrums, then you have this the value on each on one pixel, or you have average, or what does that mean?
So every pixel is a linear combination of these 200 elements. So every pixel xi, it is So it is the combination. Okay, so this is S, and then we have alpha ij.
Sure.
So Sj is S is across the entire pixel.
I see.
And for every pixel, it has aij. Which is probably
S. I see. This is S. Now AIJ. This is not AIJ.
Yes.
Fine.
Thanks. AIJ is bottom. So AIJ I have to reform it as a matrix.
Fine.
But S is yes.
Thanks.
Yeah, that's a good. Yeah, sorry, I should clarify it in the beginning. Yeah, and I also want to say that you can see the spectral estimation has nothing to do. It's very largely compared to the reference, right? So it's very different. Maybe this is a little bit better, but it's not accurate at all for the spectral estimation. But so the real data is always difficult. So we assume a linear mixing model, right? So we assume X is a linear combination of S, but in real life it may not be linear. So yeah, real data is always hard, but that is the existing work, what they can do. And also, so this also explains that although we have these quantitative measures, it may not be so accurate. So if this metric is small, it does not mean this method is good, because the ground truth spectra, they by hand label, right? So they have this data, they may hand label it. This may not be accurate either. So it just provides you with a reference. You cannot fully trust those quantitative metrics. So as you can see, this data, QMV, is actually performing very well. It can recognize the road, and it also performs very good on this piecewise constant domain. And then we find this example, this QMV, it's a very latest work. It's like published in 2020, and it's performing very good. And especially for this JISPER data, it's performing really well. And I also want to say that the time, right? Yeah, so it's slower compared to our method. Oh, okay, it's comparable to our method. Sorry, because yeah, so it's comparable. Oh, and by the time comparison, we find that graph TV is much slower compared to graph Laplacian, because graph Laplacian, every step has a closed form solution, but graph TV, you need a lot of MBO scheme, right? And then another graph method, this method, it's very slow. And then we separate the computation time in terms of graph and then in terms of the algorithm time. So this NMF, it uses a fully connected graph. So that's why the graph time is significantly slower compared to the Nystrom method. Although I think we achieve the same goal by doing fully connected graph. But if we do not do Nystrom, it will be 100 slower. Oh wait, maybe 1,000 times slower compared to using Nystrom. And also, they are although I don't know what their algorithm is doing, like the GLNF, but it's much slower compared to the QMV and also our method. Okay. What time? Okay. I think I'm almost done. So I have one more data on the urban. So that is very classical urban data. I see it like for 12 years. Yeah. So I don't have much to comment, except that maybe let's look at the roof. I think only these two have can show up the bright of a roof. The rest is pretty dark, and also this might be too much, right, on the roof. And then the contrast wise, this method is very dark. And basically this QME in general has a darker contrast compared to other methods. Yeah, so I don't have other things to look at for the urban data. And then for the quantitative measure, as you can see, the graph TV is actually, the graph Laplacian is actually the best method, because this data does not have, too much, like fine details, so that the graph TV will show advantages over graph Laplacian. Yeah, and by visually, I think graph Laplacian is indeed better, of the best across the entire, all those methods. Okay. Oh, well, one more thing before I conclude my talk. So there are so many parameters in our approach. We have sigma. We have like in the Nystrom. It's not 1%. It's 0.1%. So we only compute the 0.1% of p and to the rest of it. So that's why it's so efficient. And the sigma is to control the pairwise. We first compute the cosine angle and then we divide it by sigma, right? So there's a sigma. And then we set dt. So remember when we do the MBO, we have a time step, and we set dt to be 0.01, and we only run MBO for 5 iterations. And then the other parameter we can, there's a rho parameter and there's lambda. Yeah, I should mention about those methods. So I believe lambda is the model parameter, and rho and gamma are based on ADMM. So we think there's a proportion between rho and lambda, and we only tune rho. So we get another matrix. So I believe the first column is based on, like, we let rho, lambda, gamma choose freely. So we have a 3D search grid. And then for the second column, we fix them and only to lambda. So the second column is the degenerated case of the second column. And then by observing this, we find a better way of tuning parameter. So what I want to say is the important parameter 2 is lambda, and then we can fix in rho and gamma. Okay, so there's not too much parameter to tune as it looks like it. Okay, so finally, let me conclude my talk. We propose two methods, Laplacian and gTV for blind hyperspectral unmixing. And then we apply Nystrom method to approximate eigenvalue, eigenvector of a normalized graph Laplacian, which significantly speed up the whole process compared to like the graph non-negative matrix factorization. And then specifically for total variation, we adopt the Ginzburg-Lambda approximation, which can be solved by MBO efficiently at bitwise, at bit channel. And the future work include, as I point out, the graph TV may not be efficient on the piecewise region or relatively smooth region. So our future work is combine this graph TV and then the spatial method, say the spatial TV, to deal with a variety of structures, right, including structures of smooth regions. Okay, so that's all for my talk. Any questions?
Okay, thanks, Yifei, for this very interesting talk. Any questions so far? Question? I do have a few questions. Maybe I ask a couple, maybe just very few of them, then we can talk something offline.
Okay, sure.
So my first question is so because the W you are choosing is like exponential minus like non-local way, right? So presumably you may have some sort of approximate sparsity structure if your sigma is reasonably small. So you would say that number decay, right? So you can truncate.
Yeah.
So is that the reasonably good, instead of using the low rank but use Wij as a sparse matrix, then you can also compute.
No, we don't want. Okay, so in the local means we do have a sparse, right? Because we it's in the local, it's not fully connected. So a majority of W is 0 because it's not connected. But here we consider fully connected. But we cannot afford to compute it fully connected graph. So we use Nystrom to so our W will be a where is it? Our W will be a dense matrix. But we don't save the big matrix. We only save UV. So we only save the singular value decomposition of W.
Yeah.
We don't technically.
So
it's a low rank.
I see. I understand that part. But what I mean is because the structure of the W is exponential minus D squared, D divided by sigma. If sigma is small, that thing automatically becomes approximately sparse. So if you just truncate, nothing will change too much, right? Because that number
depends on
it depends on the distance. Depends on the dxi xj. If that number is big, then exponential minus that is teeny tiny small.
Yeah, so that's why sigma is very important. Yes, you're right.
So
if the distance square is very big, we need to choose a big sigma.
Oh, you don't want to decay.
Yeah, I don't want to decay too much. So I don't want to make W to be like a binary, either 0 or 1. Because xii is always 1, right? I don't want this the remaining thing to be too small. So this sigma is very important. It controls how similar we want them to be.
Yeah,
so sure. If we want, so sigma usually proportional to like the distance. Yeah, so we need to choose it carefully.
I see.
We don't want it to end up with binary weight.
I see. So you choose sigma to balance the distance, such as it's not the sparse.
Yes. It's not sparse.
I see.
Yeah,
The other question is, so because you mentioned this Ginsburg-Landau for the TV, why not just split one more time and then you can?
Say that again.
I mean, when you do the total variation, you can split one more time, right? Because you use ADMM either way. So why you use GL?
Oh, I think even we do it one more time, it's still you will solve total variation as an inner loop, and it may not be so efficient.
No, it's not. Well,
yeah,
but you just use one iteration of that, right? Because if you split this TV, then you get the Laplacian again.
Like, so we use here it's a Laplace. We do a Laplacian. So we do a gradient descent and we do a shrinkage.
Sure. But you can. Yeah. As you mentioned, to do this you have to do the bitwise. But if you directly do TV,
is quick.
I see.
Oh yes, okay. So first of all, bitwise is quick, and then we can parallel. And TV, yeah, I forgot why we are not directly solving TV. I guess the same reason why they do not do TV for other application. Otherwise, they can just do TV, right?